So, as I mentioned in the previous lecture, finding the sum of a series is a lot harder than determining just whether it's convergent or divergent. So, for the next few sections, and for actually most of this chapter, we're only going to be concerned with whether a series is convergent or divergent. What specifically it converges to is a different question, one that we will not focus on so much. Okay. So in 11.3, here's one of the theorems that we're going to be able to use to determine whether a series is convergent or divergent. So, this is just called the integral test. It says, let an be a positive and eventually decreasing sequence of real numbers. Okay, specifically, this is only for a positive sequence, and it has to be eventually decreasing. Given a continuous function let's call this f, defined on the closed interval from 1 to infinity, such that for every positive integer n, f of n is just the nth term of the sequence. The series sum from n equals 1 to infinity of an is convergent if and only if the improper integral from 1 to infinity of f of x is convergent. Okay? It's a long statement, but it's not too complicated of a theorem in terms of how to apply it. Let me just get a new marker here, since what I was using is apparently running out of ink. So, of course, we're going to do some examples here. So, let's start with this one. We want to determine whether the series sum from n equals 1 to infinity of ln n divided by n is convergent or divergent. Okay, and that's all I want. Okay, we just want to know whether it's convergent or divergent. If it is convergent, we'll just say, okay, it's convergent. We won't bother trying to find what the sum actually is. All right, so the way this works is, what we're going to do is, we're just going to take the function which you get if you replace all the n's with x's. Okay, so f of x, I'm going to define this as natural log of x divided by x. Okay? All I need is for this function to be continuous and defined from 1 to infinity, which it is. And also I need it to be positive, which it is. And also I need for it to be eventually decreasing. Okay? In order to show that it is eventually decreasing, the easiest way to do that in this case would be to take the derivative. So f prime of x. Well, by the quotient rule, this is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. And if you clean that up a little bit, it just looks like 1 minus ln x divided by x squared. Now, this derivative is negative if and only if 1 minus ln x is negative. Okay, so this is negative if 1 minus ln x is less than 0, or in other words, 1 is less than ln x. And by the way, 1 is less than ln x is the same thing as saying that x is larger than e. Okay? So this tells us that as long as x is larger than e, this function is decreasing. Which means that this sequence here is eventually decreasing. Great. And it's positive and it's continuous from 1 to infinity, and so we can apply the integral test. So all we need to do here is take the improper integral from 1 to infinity of ln x divided by x. Well, by definition, that is the limit as t approaches infinity of the integral from 1 to t of ln x divided by x. So hopefully you can recognize that this is a u substitution problem. If we just set u to be ln x, then du will become 1 over x dx, in which case this improper integral now becomes the limit as t approaches infinity of the integral from, let's see, ln 1 is just 0, up to ln t. Ln t is whatever ln t is. And this is just u du. Of course, that antiderivative is just 1/2 u squared. So this is the limit as t approaches infinity of 1/2 u squared, evaluated from 0 up to ln t. This is just the limit as t approaches infinity of 1/2 ln t squared minus 0. And then, of course, as t approaches infinity, this also approaches infinity, which means that the improper integral is divergent. And so by the integral test, that means the series is divergent. Okay? So we can just say, by the integral test, the series is divergent. And then we're done. Okay? And I want to point out this theorem is, well, this example is illustrating that the integral test gives us something that the regular old test for divergence cannot give us. The test for divergence would say that if the limit of the terms is not 0, then it's divergent. But for this one, the limit of the terms is 0. So what then? The divergence test has nothing to say about that. But the integral test can do that for us. Okay? So of course, we're going to do another example. All right, let's see. Next one is going to be n squared e to the negative n cubed. Once again, we're taking the sum from n equals 1 to infinity, and we want to determine whether that's convergent or divergent. So, no problem. Once again, we're going to define the function f of x, which is just the sequence, except all the n's are replaced by x's. So this becomes x squared e to the negative x cubed. And it's positive, it's continuous from 1 to infinity. The only thing left is to show that it's eventually decreasing. All right, so once again, this one, it's not so easy to tell that it is going to be eventually decreasing, but that's okay. We can take its derivative. So f prime of x, this is a product rule. So this is going to be the first times the derivative of the second. And by the way, in doing the derivative of e to the negative x cubed, we have to use the chain rule. And plus the second, so e to the negative x cubed, times the derivative of the first, which is just 2x. Now, if you clean this up a little bit, what you get here is, let's see, x times e to the negative x cubed. And then we have here 2 minus 3x cubed. Right? Just doing a little bit of combining like terms, factoring some stuff out there. So now let's notice that this is negative as long as 2 minus x cubed is less than 0. Well, okay, as long as x is greater than 0 and also 2 minus x cubed is less than 0. Okay? So this is negative if x is positive and 2 minus 3x cubed is less than 0. By the way, that's the same statement as 2 is less than 3x cubed, which is the same statement as 2/3 is less than x cubed, which is the same statement as the cube root of 3 of 2/3 is less than x. Okay? So what this tells us is that as long as x is larger than the cube root of 2/3, this will be a decreasing function, and that means that the sequence is, in turn, eventually decreasing. Okay? All right, I'm just going to erase some of these intermediary steps here. The important part is it's negative if x is greater than the cube root of 2/3. And so that shows it's eventually decreasing. And then, since all the assumptions of the integral test are satisfied, the integral test applies. So that means we can just take the improper integral from 1 to infinity of this function, and if that is convergent, then our series will be convergent, and if it's divergent, our series is divergent. So this, by definition, is just the limit as t approaches infinity of the integral from 1 to t of x squared e to the negative x cubed dx. So now this is another u substitution. We can say u equals negative x cubed, in which case du would be negative 3x squared dx. So then this now becomes the limit as t approaches infinity of the integral from, let's see, negative 1 cubed would just be negative 1, and negative t cubed would be whatever negative t cubed is. I can probably do better than that as far as my handwriting goes. That's better. Now our integrand becomes now negative 1/3 e to the u du. And so, of course, the antiderivative of e to the u is just e to the u, which means that this is going to be the limit as t approaches infinity of negative 1/3 e to the u, evaluated from negative 1 up to negative t cubed. So, this is the same thing as the limit as t approaches infinity of, let's see here, 1/3 e to the negative 1 minus 1/3 e to the negative t cubed. 1/3 e to the negative 1 is just a constant, so whatever. Now, as t approaches infinity, e to the negative t cubed approaches 0. So this whole thing just approaches 1/3 e to the negative 1, which is the same as 1/3e. Okay? And so that shows that this improper integral is convergent. If the improper integral is convergent, then according to the integral test, the series is also convergent. So by the integral test, the series is convergent. Okay? Now, and I want to be clear here, that the integral test makes no claim as to what the sum of the series will actually be. Again, that's a much harder question. This 1/3e, this is the value of the improper integral, but that doesn't mean 1/3e is also the sum of the series. It's not. Okay? All that the integral test is saying is, if this is a real number, then this is too. Okay? Which real number? That's another question. Okay? Let's see. All right, let's do another one. Okay, this one asks for the sum from n equals 1 to infinity of 1 divided by 3n minus 1 raised to the 4th power. And once again, our question is the same. Determine whether it's convergent or divergent. And our strategy is going to be the same too. Once again, we're just going to take the function that this sequence corresponds to, so that's 1 over 3x minus 1 raised to the 4th power. Now this one right here, this one is actually pretty easy to show that it is decreasing. Because, well, you can take the derivative, you can do all that and show that the derivative is negative. That's fine, that works. But also, let's just think about this for a second. 1 over 3n minus 1 raised to the 4th. Now, if you take 1 over 3 times n plus 1 minus 1 raised to the fourth. Right, so that would be the next term in the sequence, right? That would have a larger denominator, right? Because, I mean, if we were to actually do this out, this would be the same as 1 over 3n plus 2 raised to the fourth power, right? And I'm pretty sure this number is larger than this, right? Okay. Well then, if the denominator is larger, the whole fraction has to be smaller. Okay? So that is enough to show that the sequence is eventually decreasing. And in fact, this particular sequence is always decreasing. Okay, so we didn't even have to screw around with the derivative. This time, it was just easy to see. By the way, in all of these problems, I am going through this process of showing that the sequence is eventually decreasing, the sequence of terms is eventually decreasing. That is necessary. You do have to do that, and on assessments, if you don't show any consciousness that the sequence needs to be eventually decreasing, you will get points deducted, okay? I'm saying that because I know someone's going to ask me at some point. Anyway, now that we have that the sequence is decreasing, let's look at the function f of x, which is 1 divided by 3x minus 1 raised to the fourth power. The sequence is positive, we showed it's eventually decreasing, and this function right here is continuous and defined from 1 to infinity. Okay, yeah, you'll have a little bit of a problem if x is 1/3, but that's not the point. It's defined and continuous from 1 to infinity. That's all that we care about there. So, we just need to take the improper integral from 1 to infinity of 1 divided by 3x minus 1 raised to the fourth power. And by definition, this is just the limit as t approaches infinity of the integral from 1 to t of 1 divided by 3x minus 1 raised to the fourth power. So this is another U substitution. It seems like that integral technique is just our best freaking friend today. Yeah, this is another U substitution. So we just get u equals 3x minus 1 and du equals 3 dx. Now this gives us the limit as t approaches infinity of the integral. Let's see, 1 changes into 3 minus 1, which is 2. And t changes into whatever 3t minus 1 is. And now what we're dealing with is 1 over, well, there's a 1/3 out in front. So I should put that there. And the rest of this is just going to be u to the -4th du. Okay? Right, so now that antiderivative can just be done by the power rule. This is just going to be the limit as t approaches infinity of, let's see here, I guess you add 1 to the exponent, so you get -3 divided by the new exponent, and that gives us another factor of -1/3, so together with that other -1/3 we get -1/9, and then u to the -3rd, evaluated from 2 all the way up to 3t minus 1. So, this is just the limit as t approaches infinity of, well, I guess I want to rewrite this first. I guess I want to say that this is 1 over 9u cubed, evaluated from 3t minus 1 up to 2. So the first thing I'm doing there is I'm just saying u to the negative third is the same as having u to the third in the denominator. And the other thing that I'm doing is I'm negating the whole thing and flipping the bounds, which you can do. You can flip the bounds as long as you're willing to negate the thing that you're dealing with. Okay, so then you evaluate this, and what you get is the limit as t approaches infinity of 1 over, let's see, 2 cubed is 8, and then 9 times 8 is 72. So 1 over 72 minus 1 over 9 times 3t minus 1 cubed. So now as t approaches infinity, of course this denominator gets enormous, and so this whole fraction approaches 0. So then this whole thing just approaches 1 over 72. And so by the integral test, the series is convergent. So by the integral test, the series is convergent. Okay? Now, here's an important example, for more than one reason, really. So we're going to use the integral test to determine a more theoretical question. In my notes I call this an example, so I guess I'll call it example here as well. Okay. For which real values of p does the series sum from n equals 1 to infinity of 1 over n to the p converge? All right. So this series is called the p series, and well, let's look at how this works. So there are a few cases that we need to consider. First of all, it's possible that p is negative, right? If p is negative, then we have a negative exponent in the denominator, which is the same as having n raised to a positive exponent, right? And then if you just look at the terms of that series, well, the test for divergence indicates that it's going to diverge because the terms of the series are going to approach infinity. Okay? So if p is less than 0, then the limit as n approaches infinity of 1 over n to the p, this is the same as the limit as n approaches infinity of n to the negative p. And now, as I said, if p is negative, then negative p is positive, which means that this is a positive exponent, and n is approaching infinity, so this is just going to blow up. All right, so by the test for divergence, this series would be divergent. Okay, so that's just the case where P is negative. So that tells us if P is negative, it's divergent. End of story. All right. Well, next up there's the possibility that P is just 0. So let's see here. If P is 0, then this is now the limit as n approaches infinity of 1 over n to the 0. But n to the 0 is just 1, right? So that'd be 1 over 1, which is 1. So the sequence of terms is just 1, 1, 1, 1, 1, 1, 1, 1, 1, and so on. And you're adding all of those up. Hopefully, you can tell that if you just keep adding ones together, you're going to get something that's just going to grow without bound. And so that's not going to converge. And yes, the test for divergence is another way of recognizing that same thing. The limit of 1 is just 1. So again, by the test for divergence, this series would be divergent. Okay. Okay, in my notes, I don't appear to have, I appear to be missing something. So, I may edit this out and fix up my notes and then come back to this. Alternatively, I will just do it right here and right now. Okay, so what happens if P is greater than 0? All right, well, if P is greater than 0, then, well, we're dealing with 1 over n to the pth power, and we're trying to determine whether that converges or diverges. So what we can do is we can say, first of all, n to the p is less than n to the p plus 1. No, that's not what I meant to say. That's true, but that's not what I meant to say. It's less than n plus 1 raised to the p. Right? And so that would mean that 1 over n plus 1 raised to the p has to be less than 1 over n to the p. And that means that this sequence of terms is decreasing. Okay? Therefore, it's eventually decreasing, which in turn means that the integral test may apply. So we'll just look at the function f of x equals 1 over x raised to the pth power. That's continuous and defined from 1 to infinity. So, integral test can apply. So now we're looking at the improper integral from 1 to infinity of 1 over x to the pth power. Okay, so we've actually dealt with this before, but it's okay if you don't remember, we'll do it again. So this is the limit as t approaches infinity of the integral from 1 up to t of x to the negative p dx. So now, that antiderivative will have a different form depending on whether p is 1 or not. Okay. So if p is 1, which is part of this case because, of course, 1 is greater than 0, if p is 1, then this becomes the limit as t approaches infinity of ln x evaluated from 1 up to t. Right? Because the antiderivative of 1 over x is ln x, and x to the negative 1 is the same as 1 over x. So now this is just the limit as t approaches infinity of ln t minus ln 1, but ln 1 is just 0. Anyway, this is infinity. So by the integral test, it's divergent if p is 1. Okay? Now what if p is not 1? If p is not 1, and we're still saying p is greater than 0, then you can do the power rule on this. So this will just become the limit as t approaches infinity of x to the 1 minus p divided by 1 minus p, and all of this is evaluated from 1 up to t. So that would just be the limit as t approaches infinity of t raised to the 1 minus pth power divided by 1 minus p minus 1 raised to the 1 minus pth power, which is just 1, divided by 1 minus p. You can factor out the constant of 1 over 1 minus p, so you can turn this into 1 over 1 minus p times the limit as t approaches infinity of t to the 1 minus p minus 1. So now, we're saying p is greater than 0, and it's not 1. If 1 minus p is positive, though, then this is going to approach infinity. If it's negative, it'll approach 0. All right, so if 1 minus p is greater than 0, then this whole thing just approaches infinity. If, on the other hand, 1 minus p is less than 0, then this approaches, 1 over 1 minus p times 0 minus 1, which is the same as 1 over p minus 1. Okay? So, in every single case here, we get divergence unless p 1 minus p is less than 0, which is the same as saying p is greater than 1. Okay? So our answer to this question is p has to be greater than 1 in order for the series to converge. Okay? And that is important enough that I'm going to state it as a theorem now. This theorem is often called the p-series test. So this is the p-series test. It just says let p be a real number the p-series, which is just the sum from n equals 1 to infinity of 1 over n to the pth power, this is convergent if and only if p is greater than 1. Okay. And this comes with the following corollary. A corollary is a statement that's implied by another statement. The harmonic series the sum from n equals 1 to infinity of 1 over n, this has to be divergent. I mentioned that in the last lecture, but now this is the reason why. The harmonic series is divergent because it is the p-series when p equals 1. Right? This is 1 over n to the 1 right here. So, by the p-series test, it's divergent. Okay? Now the p-series test, as we've seen, is a consequence of the integral test. And so it has limited use, but it still has some use. So let's just go ahead and do a small example here. I want to determine whether the series sum from n equals 1 to infinity of n to the negative, what is that, 0.3? Yeah, 0.3 is convergent or divergent. Okay. Well, first of all, let's note that the sum from n equals 1 to infinity of n to the negative 0.3 can be rephrased as the sum from n equals 1 to infinity of 1 over n to the positive 0.3, right? Okay. And then that's a p-series. That's the p-series when p is 0.3. Okay? So, of course, hopefully you agree with me on this, 0.3 is less than 1. Specifically, it's less than or equal to 1. The point is that p is not greater than 1. Okay? So, by the p-series test, the series is divergent. Okay? All right, so that will wrap it up for today. Homework is up, so go ahead and get some practice on that.